All right, so this situation, the textbook refers to this as motional EMF. Ooh, EMF, that's this symbol. Ooh, I don't want that. This symbol right here, this cursive E, is EMF. Why is my pen not dark? Looks gray. Okay, EMF. EMF is another name for what? Voltage. It's the same thing as delta V, okay? So motional EMF, motional voltage, it's a situation like this where you have two rails and this bar that slides on the rails. So this metal rod completes the circuit. Does everybody see that? The metal rod riding on those rails, it completes the circuit. So we have this loop right here. Now, what's happening in this particular situation is we have a string that's pulling the metal rod to the right, and we're given this velocity, 1.8 meter per second. So, would this be a situation where we generate voltage and therefore current? It is. Now, the background on this, it all starts with magnetic flux. Right here I have the magnetic flux equation. Magnetic flux, you take the magnetic field, which is B, you take the area of the loop, A, multiplied by cosine theta. Theta is the trickiest part of the equation. It's the angle between the normal line to the loop and the field. What's theta going to be for this problem, for this situation here? What would this theta here be? 0 degrees, because look, the normal line to the loop is sticking straight at us, right? It's perpendicular to the loop, and then the field is going straight in. So the angle between the field and the normal line is 0, and cosine of 0 is 1. That's the maximum possible flux. The other extreme would be like if the magnetic field were coming across the loop like that. What would be the angle there? 90, and cosine of 90 is 0. That would be 0 flux because the flux can't get in. So anyway, all of this starts out with flux. Like, flux is the key idea here. Now, flux by itself, not very interesting. When does flux become interesting? When it changes, which brings us down to the next equation. So this next equation, oops, I want my box around there. So this next equation is Faraday's law of induction. And so let's go through this equation. What is N? Number of loops. How many loops do we have in this problem? 1. N is 1 for this situation. There's 1 loop. You know, if you have more than 1 loop, they'll have to tell you. That'd be like if you took a wire and you went loop, you know, 1 loop, 2 loop, 3, 4, 5, 6. The more loops you have, the stronger the induced voltage will be. Okay, so N is number of loops, change in flux. Now look, how many ways can you change the flux? You can change the flux one way. You could change by messing with the magnetic field. You could change the flux by messing with the size of the loop, or you could change the flux by messing with theta. You are going to see problems with all three, right? Like how would the magnetic field change? Well, let me close this. How would the magnetic field change? Well, the problem would have to say like, hey, so see this 0.8 Tesla field? It drops from 0.8 to 0.1. You know, there's a change in the field. All right? How could the area change? Well, in fact, that's what's happening right here. If you look at this situation, as this metal rod moves to the right, what's happening to the area of that loop? It's getting bigger. And that's exactly what's going on in this particular situation. But then theta, you could also change the magnetic flux by turning the loop, right? Turning the loop through the field. All right, so look, I want to derive an equation for you that's going to be very handy. So for this situation, we already said N is 1, so we'll just kind of ignore this N. So our equation is going to become this. It's going to be change in flux over time. Now for this situation, what did we say is causing the change of flux? The area. So this is going to become B delta A. Everybody see that? The change in flux is B delta A. and ignore this cosine theta because that's just 1. Okay, so we got B delta A over T. Now, what would this change of area be? The change of area, so let's say that the length of the bar, the length of this rod is L. So from rail to rail is L. We don't care about this and that. Why do we not care about the part of the rod sticking out over the rails? We don't care about that because why? It's not part of our loop, right? So the length of the rod from rail to rail is L, and then let's say that the rod moves a distance D. Okay? So they're calling for seniors. I'm almost done. Okay, what would the change in the area be? The change in the area is going to be this, correct? It's going to be this shaded part right there. As the bar slides to the right, this would be the change of area. Well, what's the change of area going to be equal to? The change of area is going to be L times D, where D was how far the bar moved. I kind of scribbled over it. This is D right here. It's how far the bar moved over delta T. Now, what do you notice here? What is D over T? That's the velocity of the bar. So we get BLV, not to be confused with one of my favorite sandwiches, the BLT. Okay? So don't do the BLT. You want the BLV. All right? That's how you calculate induced voltage when you got a bar moving through a field. Oh, and then by the way, how do you figure out the current? Once you got the induced voltage, how do you get the induced current? E equals IR, right? Just Ohm's law. So then I is E over R.